Hello everyone, back to my another tutorial. Right now I decided to make some kind of tutorial series about GANs. I'm not sure how many tutorials I'll make, but basically I wanted to introduce myself and you with generative adversarial neural networks. That's kind of networks where you try to generate some similar data as we use to train our model. For example, if we have batch of images of people, for example, profile images, we train our model to generate similar images, and this neural network from some kind of noise should generate a similar image where we could see some kind of person that is not real. And basically, this is going to be some kind of introduction tutorial for you to get familiar with it. What is the architecture of these generative neural networks? What's the structure? What's the idea? How it works? How they train, and etc. So I already made this kind of code you can already see, and we use it to train our networks. For introduction tutorial, I decided to make it as simple as possible, so I will use that MNIST dataset. That's kind of digits dataset where it's from 1 to there is from 0 to 9, then 10 digits, and we'll try to train the model to generate these MNIST digits. So basically, I'm using a TensorFlow here, and right now I'll go step by step in this code to give you some kind of idea how it works. But first, let's see the architecture. I have here an image where it shows us how it works. So, for example, we have two models. It's a generator model and discriminator model. And basically, we have some kind of input vector. It's a randomly drawn vector from latent space. That's we can name it noise. And we give this noise vector to the generator model. And from this noise vector, it tries to generate some kind of output image. As you can see, here is that input layer, hidden layers, and output convolutional layer that actually gives us an image at an output. And basically, what's the logic around this when we are training it? That is, our generator always generates images that are fake. And on the other hand, we have real images. So after generator makes some kind of fake images, we combine these fake images together with the real images, and we know that these are fake and these are real, and we give the discriminator these images. And discriminator tries to tell us whether how well these fake images are similar to real images. This means how real these fake images are, and we try to minimize this distance so that our discriminator thinks that their fake images are real. In this case, we are training generator model according to the feedback from the discriminator, and this way we are generating this over and over, and at the end we have very similar images to our training dataset. And but these models have one huge drawback, that they require a lot of training time and they require a lot of computing resources. So if you don't have a GPU, I think it's pretty impossible to train these because, well, yeah, they require a lot of computing power, and of course they require a lot of training time, especially if you are dealing with huge resolution images. You'll see that now in my example I'll go through images that are 28 by 28 size with MNIST. But in the future, when we understand how everything works, we'll try to grab hard images like faces, and we'll try to train it. We'll see how long it trains, how well it works, and etc. So right now, this is the whole logic, whole structure, and etc. So we can begin with the code. As you can see, here I have an MNIST load dataset. This is a MNIST dataset from TensorFlow dataset. So make sure you have a Python 3.10, and I'm using TensorFlow 2.10. And here is the MNIST. As you can see, I'm importing this from dataset. In a second, we'll cover everything else we have here. So basically, I hope you can hear me. I can move my microphone closer. Okay. Great. Let's see. So first, I'm loading an MNIST dataset. I think it's not necessary to look at it because it's pretty clear how it looks like. And the idea here is that we need to normalize this training dataset to be between -1 and 1 because when we load it, it's an uint number from 0 to 225. So we need to shift them to fit them into -1 and 1. And in a moment, I'll explain you why we keep it between -1 and 1. So next, we decide what will be our image shape. It will be 28 by 28 and 1 at the end because it's a grayscale image, one channel. Our noise dimension will be 100. We decide where we'll save our models, and etc. So it will be in my models, GANs, introduction, tutorial path. And of course, I make sure that this path exists and I'm creating one. So now I need to create a generator and discriminator models. So let's go into my models file. And first, as you saw before, generator generates images from a noise vector. It's some kind of noise dimension as we input it here. And you saw that it's 100, I set it 100, and from this vector we are creating an image as we require. This means that we need to rely on the architecture and to make sure that our model outputs the specific shape that we need. So this means need to be accurately modifying our model, how it upscales the images. Because here we are using a dense, for example, image to create like a huge dense vector. And then we reshape it into the image. Now, so in this case, it has this image 7 pixels by 7 pixels and has 256 channels depth, and then we move on. So I apply the convolutional networks, and as you can see, I'm not using any strides. This means I'm not changing the dimension of this. Next, I use another upscaling vector, and right now it should double here. So I'm upscale it, and right now I apply another convolutional layer that is with strides 1 by 1, and then you can see that my shape of output is 14 by 14 by 64. That's pretty close to what we expect to have. And then I apply one more additional upsampling block, and in this case, we are receiving the 28 by 28. And you remember I said we need to normalize the input images but between -1 and 1. This is because we are using activation of tan-h. And this activation kind of gives an output between -1 and 1. So this means that our input images should be the same as the output images. Of course, it would be possible to use a sigmoid activation that gives us output between 0 and 1, but well, we have more option states when we expand this between -1 and 1. Simply, instead of having 100, we have 200 options in it. So that's great. And now you can see that our generator is pretty simple. We give it one noise dimension and we have an output of an image. So now, what is the discriminator? So discriminator is also pretty simple. It does it reversal stuff. So if we give it an image, we need to downsize this image to have one output. It's a sigmoid output, and it will be a probability whether it's real or fake image, as you can see, because I'm downsizing this image, and at the end I'm having flattened all the vectors and receiving a dense of 1 and using sigmoid. And basically you don't need to rely on this architecture. It definitely could be better, but because we are using pretty simple dataset, it's not the goal in this tutorial for us to focus on the architecture, because the dataset's pretty simple. Our model should particularly understand and learn what it needs to do. So great. Next, we move back again here. So here we build these two models. And then we set the generator optimizer and discriminator optimizer. Well, we set it as usual, Adam optimizer. We set a pretty low learning rate. And if you are first time looking at this, you might see that we set beta 1 parameter, and it's pretty common to generative adversarial neural networks to change these parameters. Well, we are not going deep into it, but that's basically math, why we do this. I'm not going to explain here because I'm not fully confident why we do so, but we need to do so because it has more stable training stuff. We are creating two TensorFlow callbacks. We'll come to this a little later. And next, we need to generate this GAN model. So why we do this? Well, basically, in standard way, when we are working with a TensorFlow, we simply generate a model and we pick a data set and call a fit function on this kind of model. But right now, when we have two models, there's a kind of some misunderstanding how we train two models if we don't know how to combine this stuff, how to use fit on two models. So basically, here comes the custom implementation of this generative adversarial networks to combine two of these. By default, this also standard models use this implementation, but instead they have a standard way to use this with one model. So we need to inherit everything from this kind of model and use it. And here, as you can see, I'm feeding the generator, discriminator, and I'm feeding the noise dimension to this kind of model. And this will create us the training pipeline. So idea here is that we'll call compile on it, but on compile step, we are feeding these kind of optimizers. Instead of one optimizer, we give it two optimizers, and we give our loss function. We'll come back into this also in a moment. And then we simply have a train step. That's also default way how it works. But differently, right now you can see that we feed a real images, that's a batch of images, and we need to know what is the count of our batch. So we could create a random noise dimension for our generator. So we do this here. And then we are calculating the tape of discriminator and generator. So basically, first step is to generate fake images of the generator. So next, we need to predict real and fake images get the results from discriminator. So first we give it real images, and then we give it our fake images. And we know whether that at the end these should be pretty similar outputs, but when we start training, they are pretty different. These kind of opinions, whether it's real or bad. And then we are calculating the loss between generator and discriminator. And then we are using backpropagation. Then we apply these gradients on the generator and discriminator models, and we repeat this over and over. And for simplicity reasons, I added these metrics callbacks so we can use TensorFlow metrics in a standard way. You'll see that it's really useful. We don't need to implement any additional custom stuff. We can follow the TensorFlow rules and implement it in our way. So you might ask, okay, but what is the loss functions for generator and discriminator? Well, it's pretty easy. Here we go up. I have here this defined discriminator loss and generator loss, as I said. And discriminator loss takes the real outputs and fake outputs. And we are trying to calculate the differences by using binary cross entropy. And as you can see here we give it a real image samples, and here we give it a fake image samples. And we try to minimize these differences, and we sum these losses, and we have a total loss. That's nothing magical, actually. And Also, we have a generator loss, and you can see right now that we are not incorporating the discriminator. So here we are simply giving a fake output that basically output from a generator. We always know that it's fake, and we try to improve it simply by telling that it's fake, give us better ones, and that's it. And yeah, let's go down here. Okay, so now you know how I created these kind of losses, discriminator loss and general loss that we feed into compile. So as you can see here, here's optimizer, Adam, this optimizer. I have a run eagerly option here, so this was only for debugging reasons. When we turn it as true, it's way simple to understand what it does because we can step into the loss function, into custom training loop, and etc. So, and the last step is we simply call a fit on our MNIST dataset images, and we can change this batch size. It depends on your capabilities of GPU, and if you don't have strong GPU, you might lower this. I am able to run this with 128 samples from our dataset, and I simply use it. I run this for 100 epochs. As I said, it requires a lot of batches, a lot of time to train, and etc. But, well, you might ask, how do we validate our model? For example, how we know that it's training, it working, how good the results are. And here comes the disadvantages of these generative networks, that there is no easy way to track how it trains, basically. Even with our harder tasks, it's pretty challenging to find the solutions that we could use as validation loss, because both networks are training at once and competing with each other, and there is no clear way how to validate them, and usually they might be overfitting, having vanishing or exploding gradients, and these are the main disadvantages of these networks. But because this is pretty simple data set, we are clear and we know that it's gonna work, at least for this example. And for this reason, I created these kind of callbacks. So one is the TensorFlow callback that we're gonna track our results from a training process where we hit a discriminator and generator losses, and we'll record them on the TensorFlow. And the next second is the results callback. That's kind of custom callback that I implemented to save images after each epoch. So this means that we'll save the images from generator when epoch ends. And what we do here, we feed what's the noise dimension, where we want to save it, how many examples there will be, grid size, spacing between images, and GIF size. And the GIF will be generated at the end of the training loop. And basically, what we do here, that at each epoch end, this kind of function is called, and as you can see here, that I have a self seed that was created on init. This means that I am using a single seed of the noise, and this means that every epoch our seed will not change and it will be constant, so we'll be able to see from the same noise how our images evolve. For example, if this would be the faces, you would see how network is training to generate better and better face, well, from noise, how it reshapes the face to get better view of it. So basically, that's the purpose. And then we are simply getting these predictions. We transform them into the image from -1 to 1. We simply rescale, reshape them, and we call the save prediction function. And what this does is simply, this is already an batch of images, and we simply feed this to this function, and this function simply saves these combines these images into one single big image and saves this on disks into results folder. And as you can see, I'm using CV2. I resize it to my shape I would like to see it, and that's it. And at the end of 100 epochs on the train end, it calls the image IO library and saves a GIF image from combination from the 100 images. And if I would open these results, I already trained the model. As you can see, I can open it, that it's okay, let's zoom it. You can see that pretty huge noise, and it's who knows what it's here, but it should be an MNIST images. And if we go to few another images, for example, we can start seeing that it starts to look pretty similar to some kind of numbers, and that's pretty amazing. And if I go to image 10, for example, it's already images with some kind of noise. It's a digit. If I go to epoch 20, it's also the same, and that's pretty amazing. And if I go next, it still gets better and better. And let's go to the end, and there's output GIF that we could open, and you can see this combination of 100 images, and it creates this kind of GIF and shows us how our generative model evolves and what is the last image it generates. That's one of the ways how to validate if our generative model works. And that's it. And you might see that I'm not sure, but I think I'm not saving this model because it's pretty simple, and I haven't saved the models of Discriminator and Generator, because you can train them by yourself by using my code. But it takes, I don't know, it took half an hour or 1 hour to train it, but we can check this on TensorFlow because I have a logs here from the training results. So I already have a TensorFlow open here from my log directory, and I can open the Brave browser, and you can see that here is the discriminator loss and generator loss for 100 epochs. So let's maximize this, and as you can see that discriminator. What's the discriminator? Well, discriminator tries to tell whether it's true or bad image, real or false. And the idea here is that it should decrease over time when it trains, and that's exactly what we are seeing here. And usually when we talk about generative networks within the generator, its loss function usually might wiggle a lot. It's really hard to understand why, and simply in the best case, both of these graphs should decrease, but right now, because data set is pretty simple, generative model is pretty simple, we can see that it is increasing, but we don't care about this right now, because who cares if our images are getting better and better. But usually when it's increasing, it tells that it's overfits. It needs more various data, but MNIST, we can't do this with MNIST. We need some kind of different data set, and we'll do this in the future tutorial with another data set. So basically you can see that it works, and these curves looks like that. Let's see how it looks in relative, how long it took me to train. I think I can tell wall. So yeah, it took me from 310 to 335, so it took me 25 minutes to train. So it's not too long, and I think that's pretty good results. But I'm more fan of this to see how every epoch looks like and etc. So that's it, and this is how we train the GAN networks, and it's pretty simple and obvious. And let's look again at our GIF model. Let's go to this one. And I'm really amazed. That's the beginning where everyone should start investigating about GAN networks, and it's pretty obvious how it works right now. We have two networks, they compete with each other and try to improve both of them. And we simply generate the output of these networks using standard ways in the TensorFlow, how it's recommended, and etc. And we can see that it works particularly, and we can use it wherever we want. It's really hard to tell where we should use this example with MNIST. It's not very obvious, but when we go to harder solutions, you'll see that it's way better. So that's it with this tutorial. This is a short introduction to the Generative Adversarial Networks, and I try to cover this as quick as possible. The code is on the GitHub. You can check this, follow it, clone it, try it by yourself, and etc. And in the next tutorial, we'll cover this with a more harder task. By the way, I should mention that it wasn't that simple in GANs. We can tell this that this was DCGANs, deep convolution neural networks, because simple GANs is simple dense networks without any convolution, and it would work, but it would be way harder to train this. So I used deep convolutional networks. And in the next tutorial, I'll cover a harder task, and I think we'll move to harder architecture, some kinda. I will cover it later, but right now, that's it for this tutorial. I hope this will be useful for you. You can use it, share it, and use my code, of course, if you want. And don't hesitate to like this video, share, subscribe to my channel, and I hope this tutorial will be useful for you. And thank you again for watching, and we'll see you soon in our next video. It takes a lot of time to debug these GAN networks, and I would like to give you a final solution without any bugs and etc. So it takes me a little longer to develop them. So thank you again for watching, and we'll see you in the next video. Bye, my friends.